In IIT-JEE examination, one of the important most chapters in physics we have is current electricity, and that is related to DC circuits. Every time, of course, we people are getting few questions from this chapter. Let us today discuss about some of the concepts or important most aspects of this particular chapter, current electricity. In reality, current electricity, when we talk about, we deal with the concept of Ohm's law. According to that one, of course, the potential difference and current, how they are related, will be knowing. The current across a conductor is directly proportional to the potential difference across the terminals of the conductor. That's what actually we used to say as Ohm's law. And we in fact know well the equation for that one, V is equal to IR. I being current over here and R being resistance. Therefrom, of course, we write that R is equal to V over I. In fact, this concept is very common, and every one of you can even understand that Ohm's law is not a universal law. That's one theoretical point one has to understand. It's not going to be valid in every conductor. Like whenever we just plot a graph between voltage and current, we actually supposed to get a straight line passing through the origin. Whereas in some of the cases in semiconductors, in thermistors, we'll never used to find this Ohm's law obeying as it is like. So one should understand that Ohm's law is not universal law. This point, of course, is known to every one of you. So these aspects what we are talking about under Ohm's law, we can directly estimate and explain by taking this equation R is equal to V by I. Based on that, how this resistance that varies, we people used to calculate. In fact, resistance is directly proportional to temperature of the conductor. When we take a conductor, when temperature of that conductor increases, automatically the resistance of that conductor also increases. What is the equation we used to write for this? At 0 degrees centigrade, for example, the resistance of a conductor is R0. When we increase the temperature to T degree centigrade, let us consider the resistance is becoming RT. Now in this particular case, RT will be greater than R0. So what is the relation between these two quantities now? We write that RT is equal to R0 into 1 plus alpha into T. What is this alpha again can be written as delta R, that is change in resistance, by R0 into T. That of course you can rewrite it like this as RT minus R0 by R0 into T per degree centigrade. This is one of the important most equations one should remember as far as this chapter that is concerned. But what is this alpha now called here? This alpha is called as temperature coefficient of resistance of that particular material, we call it. Temperature coefficient of resistance, when we talk about, one or two important most points theoretically one has to remember. This value of alpha, when we take, it will be positive for ohmic resistors. That is one point you have to remember. Ohmic resistances, the value of alpha will be positive, whereas alpha is going to be negative for non-ohmic resistances as such. This is one point you have to remember. In addition to that, as the value of temperature increases, you can all understand in this regard, temperature increases, resistance also increases for conductors, which are in fact we call them as ohmic resistors. That is the point you have to remember. Whereas when temperature increases, the resistance decreases in the case of semiconductors. For semiconductors, that of course you can write this way, they are coming under the category of non-ohmic resistances as such. So these are the basic theoretical points one should remember as far as the value of alpha, which is called temperature coefficient of resistance, that is concerned. In the same manner, how we can change the resistance of a conductor? Not by considering the effect of temperature there. In fact, we all know very well, resistance is now depending mainly on two factors as far as the conductor that is concerned. What are those two factors? Resistance of a conductor depends mainly on two factors as far as the conductor that is concerned. What are those two? The very first one, in fact, we know resistance is directly proportional to length of the conductor, and it is inversely proportional to area of cross section of the conductor as such. This area of cross section we represented by the letter A and length as L. In this regard, resistance can be written as rho into L over A. This rho is called as resistivity. You can definitely understand this also can be called as specific resistance. Specific resistance. Theoretically, there is one point we have to remember related to this resistivity, that is rho I am talking. So rho is nothing other than RA by L, and of course ohm meter the unit. We all can understand directly like that. But resistivity, excepting on temperature, it does not depend on the dimensions of that conductor taken up. This is one of the important most aspects we have to remember. Sometimes they may ask you a question this way: if area of cross section is doubled of a conductor and length is made half, then how many times this value of resistivity of that wire that varies? In fact, our answer is supposed to be it does not vary. What for we can understand? When length is becoming half, automatically resistance of that conductor also becomes half. When area of cross section is becoming doubled, then also the resistance of the conductor becomes half. Now in these two cases, ultimately resistance increases by 4 times. Then naturally this total resistance decreases by 4 times, and A by L, that of course becomes 4 times. So that gets cancelled, and RA by L, that remains constant always. Remember this point thoroughly. So rho is the resistivity. It does not depend on the dimensions of the conductor. Remember that point carefully. That's one area we have to stress much on. Now come to the second one here. By changing the length and the value of area of cross section, how the values of resistance of that conductor, they vary also you can understand. One I just give you in this regard. Suppose if length increases by n times, then you directly can understand resistance now becomes how many times? N square times. Observe this concept carefully. Resistance becomes n square times. What for? L is increasing n times. How can we increase that? By stretching that one, I am increasing the length. When I increase that length by n times, the area of cross section becomes 1/nth of the original value. Due to that reason, you will be finding the resistance becoming n square times. Likewise, of course, if you take the next one, if area of cross section is increased by n times. Area of cross section, how can you increase that one by n times? By compressing the total length of that conductor, you can increase the area of cross section. So area of cross section, suppose is increased n times of the same conductor. Then what is the very meaning of that? It's very clear to say that length is becoming 1 by n times. So ultimately, what do you find here? Resistance that now becomes how many times? 1 by n square times. That is actually the concept you have to remember. Resistance now becomes 1 by n square times. That is another point what you have to understand. Exactly in the same manner, the third one, if they say radius of cross section of the conductor is increased n times. Radius of cross section of the conductor is increased n times. When radius of cross section increases n times, automatically we can understand that area increases by n square times. Then what happens? The length part of that one decreases by n square times. That in the sense what? Length simply becomes 1 by n square times. That is the concept. Then overall what do you find here? This all implies resistance now becomes 1 by n power 4 times. That is actually the concept what you need to remember. Come to the next aspect over here, the fourth. If I say resistance, how it varies with respect to length in terms of the percentage variation of length. I'll just give you one example here. If length increases by x% of a conductor I am talking about. When length increases by x%, then you can understand the resistance increases by 2x% roughly. 2x% you can understand provided if x is less than or equal to 5%. That is a value what you need to remember here. If length increases by 2%, for example, resistance of that conductor increases by 4%. If length increases by 3%, that becomes 6%. If length increases by x%, the radius, the resistance increases by 2x%, provided x is less than or equal to 5%. Suppose if I say x is greater than 5%, then the resistance increases by 2x plus x by 10 whole square percent. This is the shortcut equation which of course can make you get the result directly without much of a calculation. I repeat once again, if resistance increases by if length increases by 5% or more than 5%, that's what actually I am talking about. If length increases by x%, where x is greater than 5%, then resistance increases by 2x plus x by 10 whole square percent. For example, length increases by 20%, for example. Then 20%, 2 into 20 now becomes 40. 20 by 10 now becomes 2. 2 square, 4. 40 plus 4, 44% that now becomes. So, whenever length increases by x%, you can decide the answer by taking two separate conditions for that. One, if x is less than or equal to 5%, then resistance simply becomes 2x%. It rises by 2x%. If x is more than 5%, that of course we can take it like 2x plus x by 10 whole square percent. So these are the things what one has to remember as far as the variation of resistance depending on length and area of cross section of that conductor when that is stretched or compressed, that is concerned. When we take resistivity of a conductor, how that varies with temperature also is one of the major concepts of this chapter. When we discuss about rho, which is R A by L ohm meter, then we can understand, say at 0 degrees centigrade, if the resistivity of that conductor is rho naught, and at T degree centigrade, the resistivity let us consider as rho T. Then what is the relation between these two quantities? Rho at T degrees is equal to rho at 0 degrees into 1 plus alpha into T. Now in this regard, you can even rewrite the same equation as alpha is equal to rho at t minus rho at 0 by rho at 0 into t per degree centigrade. That is the equation what one has to remember. Now in this regard also, alpha is to be called as temperature coefficient of resistance. That is actually the value alpha that is representing here. So this equation almost is similar to the variation of resistance with the temperature. Therefore, whether it is resistance of the conductor we are considering or resistivity of the same conductor we are considering, in both the cases the influence of temperature that remains same. So that way we can remember both the equations easily. That is one area. Now come to the next case please. What exactly is the resultant or effective resistance when resistances are connected in series and in parallel? What are the parameters which are going to be variables there and which parameter that remains constant in each of the cases? Those things also are equally important for us while discussing about different electrical circuits.